Thank you all for being here. I will be presenting my work on stochastic switching in delay-coupled oscillators, comparing stochastic delays and additive phase noise. And as you can see, this was joint work with the organizer of this mini symposium, Vladimir Klinshov, and with Dmitry Shapin, both from the Institute of Applied Physics in Nizhny Novgorod, Russia. So we work with pulse-coupled phase oscillators. That is a simple and popular model for mainly for biological oscillators, mainly spiking neurons, but also to model circadian, cardiac, or respiratory rhythms. And it's also used to model communicating agents that send pulses to each other or wireless networks. Typically, those networks are delayed. Why? Because it takes time to travel from one oscillator to another. Phase oscillators always are a weak coupling model, meaning that the motion on the limit cycle is simply reduced to the phase. And the pulse coupling means that the oscillators receive a pulse, and depending on their instantaneous phase, their phase is forwarded or delayed, depending on the phase response curve, PRC. It's also a popular model with experimentalists. Why? Because, you can simply give a pulse to an oscillator and then measure the phase response curve by measuring the difference in interspike intervals. So the model that we consider is the following. The phase here moves with a uniform frequency, 1, that is normalized to 1, and as soon as the phase reaches 1, it emits a pulse and it is reset to 0. And that happens at the spike time Tn. Then a delay time tau later, the oscillator receives its delayed feedback, and depending on the phase phi at that moment, the phase is, there is a phase shift equal depending on epsilon, the coupling strength, and the PRC Z of phi. And typically what is measured for such oscillators is the phase response, the interspike interval, or the spike timings. Now we concentrate on the regime with regular spiking solutions, meaning that the interspike interval is constant. Now, such a regular regime is characterized not only by the interspike interval, but also the capacity, C, which is the number of spikes that are stored in the delay line, or equivalently, the number of completed cycles within a delay interval. And then the reception phase, psi C, which is the phase of the oscillator when the spikes come in. And obviously the interspike interval is related to the reception phase with the phase response curve. Now, typically those multiple solutions coexist. As for example, this is here for a delay time of 3. And a phase response curve that is a sine curve, we have coexisting solutions with a capacity of 3 and a capacity of 2. Here the solution with a capacity of 2 has a reception phase which is close to 0.25, which corresponds to a positive PRC, so a shorter interspike interval, and indeed within a delay time here, after a delay of 3, the first spike is received. We have 1, 2, 3 spikes in a delay interval. Same thing here. We have, for the capacity of 2, we have a reception phase of 0.8, corresponding to a negative PRC. So the interspike interval T is becoming larger, and we have only 2 spikes within the delay interval. Now, this number of coexisting solutions, as is more often the case with oscillatory systems with delay, is increasing with the coupling strength and the delay time. And now we introduced noise in the system, and that causes a mode hopping between these different solutions. Now, we introduced two different types of noise. The first, here in orange, is what we call phase noise. It's simply an additive noise source to the phase evolution, and that is the typical, usual implementation of noise in dynamical systems. Then we also implement here in blue stochastic delays that accounts for a variation in the traveling time of the pulse. And you can imagine that that is fairly common in real life systems, but it is not very often modeled in dynamical systems because it is very hard to implement in continuous coupled systems. But we have pulse coupled systems, and because our coupling is discrete, it is an ideal system to study the effect of stochastic delays. And well, what do we see? As I told earlier, the main observable are the interspike intervals. But looking here, this is the time trace of the interspike intervals, and you don't see anything. And also not in the distribution of the interspike intervals. But after applying a moving average filter with a width that is more or less equal to the delay, you find indeed events here of clear hopping between a solution with a period 1, then here a solution with a period 0.99. This is for a large delay, which is why the differences are so small. And then in the simulations, there's an even easier way to detect a mode hopping, at least for our choice of here a sinusoidal PRC. You have a switch when the capacity changes or when the reception phase here becomes larger than 1 or smaller than 0. So then, looking at the distribution over the different solutions. This is here for phase noise, and we looked at a solution with like a delay of 62.5. We have solutions with capacity 61, 62, 63. And here, increasing the coupling strength, what we see is we have the same three solutions, but the peaks, looking at here reception phase plus capacity, are way sharper when we increase the coupling strength. But the distribution itself has the same width. We find the same three solutions. And another thing we see here is a slight asymmetry as the coupling increases. Then here, if we look at the stochastic delays, what we see is that when we increase the coupling strength, we see more solutions, a wider distribution. But in both cases, the distribution is more or less symmetric. Now then, looking at the lifetimes, we compare here the lifetimes of always the central solution, because that central solution has the same frequency and the same reception phase for all parameters. And well, what do we see here? That if we increase the coupling strength, the lifetime of the central solution for phase noise is increasing almost exponentially. This weak coupling approximation is an approximation as constant coupling, and the theory for constant coupling predicts an exponential increase. Then if we look here again at the stochastic delays, we have the opposite. We have here something that looks more like an exponentially decreasing solution with the coupling strength. Now, I don't have time to go in details about the theory, but if we came up with a linear theory to qualitatively explain the scaling. Briefly, if you linearize the variation of the phases and the reception phases and the interspike intervals around a single solution, and you linearize the PRC, the system reduces to a couple of coupled autoregressive systems with the order of the capacity. You can compute then the variance of the reception phases. And then from the variance, you can relate and the variance again in approximation to the lifetimes by assuming that the probability that the phases becomes larger than 1 or smaller than 0 is proportional to the inverse lifetime, which leads to a lifetime that scales exponentially with the inverse variance. Anyway, we found that the variance consists of a term relating to phase noise plus a term relating to stochastic delays. For only phase noise, we have here that lifetime scales inversely with the variance, which means that the lifetime starts scaling exponentially here with the denominator, which has here the coupling strength. And this is pure exponential scaling as long as the coupling is small, and we can ignore this term here. While the delay here does not appear in the lifetimes. Now for stochastic noise, only taking this term into account, there we have a scaling here with 1 minus epsilon, which explains here the exponentially decreasing lifetime with the coupling strength. Now, from the lifetimes, assuming detailed balance, you can go to the variance of the overall distribution, which then scales with epsilon times tau times the variance of a single peak, which results for phase noise into epsilon here for low coupling simply cancels, and we have a scaling with the variance with the square root of the delay time, and no more scaling with the coupling strength. Then for stochastic delays, we have this variance here, meaning that we have again a quadratic scaling with a delay, which comes in here, and a scaling that in a variance that increases with epsilon. So we also did an electronic experiment with the electronic version of a Fitzhugh-Nagumo oscillator with delayed feedback, meaning that the oscillator emits a spike when coming at this point of its cycle. These spikes are stored in a shift register of an FPGA and then fed back to the system after a delay time. Now, this is an ideal system to implement both types of noise. We can implement phase noise as simply a noise source in the electronic circuit, so to the oscillator, and we can implement stochastic delays by randomly shifting the position of the spikes in the delay line. And we have some control over the coupling strength by the pulse amplitude of the pulses that the oscillator receives when a spike arrives. And we see indeed here that the mean lifetime increases with the coupling strength for phase noise, and it decreases for stochastic delays. And with that, I come to my summary. We studied a pulse-coupled oscillator with delayed feedback, and we compared two types of noise, phase noise and stochastic delays. For phase noise, we found that the system typically stabilizes longer lifetime with increasing coupling strength, while we found that the system destabilizes with increasing coupling strength for stochastic delays. So the stability, the lifetime of the system really depends on where stochastic perturbations are applied. And we have a linear theory that provides a qualitative explanation for this scaling, as well as an electronic experiment confirming it. And with that, I thank you for your attention.